Baeyer Villiger oxidation is the oxidation of ketones to esters in the presence of peroxyacids or peroxides. The reaction can be applied to cyclic ketones, which are converted into lactones under the same conditions. In this video, we'll talk about the reaction mechanism. In this video, we'll talk about this transformation and see how the reaction proceeds stepwise. So let's begin. So what happens in Baeyer Villiger oxidation is that we have a ketone here. And just for understanding, I have labeled these R groups as R1 and R2, so you can differentiate between the one that is migrating in this reaction. This ketone is treated with a peroxyacid and it is converted into an ester. If we have a cyclic ketone like this cyclopentanone, and it is treated with peroxyacid, this cyclic ketone will be converted into a lactone. And because an oxygen is inserted, this comes with ring enlargement. So a 5-membered cyclic ketone is converted into a 6-membered lactone. We'll see its mechanism in a while and see how the reaction proceeds. As the name indicates, it is an oxidation reaction. So a ketone is converted into an ester. There is incorporation of an extra oxygen. That means oxidation. So somewhere reduction has to take place to make it a redox reaction. So we have this ketone here and it is treated with a peroxyacid, which looks like this. And because it can act as an acid, so this oxygen of the ketone will be first protonated to yield a peroxyanion, and this protonation actually activates this carbonyl carbon or the carbonyl group, in other words, and we have the formation of this peroxyanion. This peroxyanion then attacks the carbonyl carbon, which of course is electrophilic in nature and is activated by the acid to produce this species. Now this species that is formed here goes through a rearrangement process, which is initiated by the shifting of this lone pair on oxygen between the carbon and oxygen, allowing one of these R groups to migrate along with their electron pair, that is the bonded pair, in the form of a nucleophile and attack this oxygen here. This in turn breaks this oxygen-oxygen linkage, releasing a carboxylate anion. So what we have now in the system is R2, that is directly attached to the newly formed carbonyl carbon, which still has this hydrogen attached to it, and this carbonyl carbon that is formed here has oxygen attached to it, and this oxygen now has R1 attached to it like this. And additionally, we have the formation of this carboxylate anion here, which is formed from the peroxyacid. This anion then takes up this proton, and as a result we have the formation of this ester, and a carboxylic acid. So as I was saying in the beginning is that this is an oxidation reaction. A ketone is oxidized to an ester, or it is converted into an ester, which is of course an oxidation reaction. So somewhere reduction has to be taking place, and that reduction has actually happened in the peroxyacid. You see there are 3 oxygens in the peroxyacid, and this peroxyacid is now converted into a carboxylic acid, which actually is a reduction process. So it is basically a redox reaction in which ketone is oxidized to an ester and peroxyacid is reduced to carboxylic acid. Now, a very important question arises here is that if you look at this mechanism, we see that this is actually the migration of R1 from the carbonyl carbon to the oxygen, which means that R1 has rearranged in this reaction. So why not R2? Why we have rearranged or migrated R1 from one position to another in the molecule? Why not R2? In fact, R2 can also migrate. And this depends upon the migratory aptitude of these 2 R groups. The one with a greater migratory aptitude will migrate, and the other will remain intact at its original position. We will talk about the migratory aptitude some other time. This is it for now. Thank you so much for watching. Stay tuned for more named organic reactions.